Welcome, everybody. This is the third live workshop in a 7-part series on supervised machine learning in Python. Today, we're going to take the fine-tuning that we did last week with feature engineering. We're going to take the original regression model that we did and get a lot better predictive outcomes based on some of the techniques that David has been teaching you. My name is Alex Chisholm. I'm the co-founder of DataQuery. We're a website that services thousands of data science learning opportunities for you to build your data science skills and develop your data-centric career. As always, I'm joined by my co-founder and data scientist extraordinaire, David Sponsor. How are you feeling today, David?
I'm feeling great. Thanks for asking.
Good. What I wanted to do before you get into your new material, I wanted to take a few minutes just to go through some of the resources that we have around this workshop series. Because now we've had more than 200 people that have signed up for either the first, second, or today's third workshop. So thank you if you are back again with us and you've looked at the previous videos, the previous code and data. If you haven't done that, let me share my screen with you quickly. You'll see that on our site right now, and I'll post these links in a few minutes in the chat box. We have a blog that goes through what we're doing in this whole workshop to begin with. We're starting out with the first 3 sessions dedicated specifically to regression analysis. So we built one the first week, then we started to get into feature engineering last time. And then today we're going to put these 2 things together and really try to get that value out of that prediction model that we're putting together. Next month, when we're going to get together for workshop number 4, we're going to get into classification for the first time as well. So from this site, you're going to be able to get the links to the old recordings or register for the upcoming events. We also have standalone pages for each of these, where you're going to be able to click and download the code, get to the interactive workbooks, find the original data set that we're doing to make these predictions in the first place. I also encourage you to check out our channel on YouTube. Because we're putting up here short videos from each workshop as well that are condensed. So we've been talking for 60, 70 minutes. We're squeezing that into 3 or 4 minutes that you might want to look at if you're trying to catch up with the series pretty quickly. So I think with that in mind, I'm ready to hand over to David right away because we've got a lot of material we're going to get into tonight. If you have any questions along the way, if you are with us on Zoom right now, feel free just to use the Q&A functionality to get in there and ask any question that comes to mind. I will either answer myself or I will interrupt David to sort of give his perspective. If you're on YouTube, just throw it into the chat box and we'll do the same thing there. So without any further ado, David, you want to go ahead and kick off the new material?
Yes, thanks a lot, Alex. Let me go ahead and I will share my screen now. So for those of you who are coming back, we are continuing today. Last session, we focused heavily on feature engineering, and we ended last session with looking at how to build pipelines with Scikit-learn. So it's a really powerful way to bundle up multiple steps for pre-processing your data into a single object. That's what a pipeline was designed to do. And then you could easily transform new data with it once you train it. So it's a very powerful feature of Scikit-learn. And so today, what I wanted to do was to review that last step that we took in the last lesson, kind of set things up with our data again, and review what our business objective is. And then today, we're going to take it one step farther. We're going to add a model as the last step into our pipeline. So now we're going to be able to bundle feature engineering and our modeling into a single object. And then we can go ahead and use that to make new predictions for new data. So it's a really cool ecosystem that Scikit-learn has built out for us. So I'm excited to show you how to do this. So here we are in Deep Notes. So now I'm in notebook number 3 of our series. And this one is called Fine-Tuning Models and Pipelines with Scikit-learn. And the first code in this notebook is going to bring in all of the functions we need to execute all the various steps that we're going to go through today. So I always like to, like I mentioned before, kind of bundle these imports into top high-level categories. So usually I start off with bringing in things like pandas and numpy for data analysis here at the top, and setting some parameters to make the printing look nice in the notebook. And then we're going to be using Seaborn and Matplotlib, again, for data visualization today. And then for machine learning, so this is where I'm going to be bringing in things from Scikit-learn and also Feature Engine. So that's the feature engineering library we went over last lesson. So if we execute this, it's going to just set up our environment, load up all of our libraries, and we'll be ready to go. So today we are going to focus, I always like to bring up this visual here of the data science process. So last time we focused on the data preparation step almost entirely the whole time. And today we're going to move into the modeling step. And notice these two arrows that kind of go back and forth between data preparation and modeling. So whenever you're working on a machine learning project, you will find that you will go back and forth quite a bit between these two steps. You'll do some feature engineering, you'll try it out, you'll see how your model performs, and then you'll think maybe, if I try this different engineering step, or if I create a new column, it might improve my performance. So you kind of go back and forth quite a bit in this stage. It's a very iterative process until you find a model that works really well or meets your business objective. And so just a quick review of what we're trying to accomplish here. It's really important to start out with the business understanding and have a clear success criteria. We have data here that I'm going to load, our wine data. And let me go ahead and display it here. So each row on this data set represents a bottle of wine that has been scored by experts. Okay, so we have this quality score, that's our first column, and that is what we're trying to predict for an owner of a winery. And for them, it's very important that the predictions are accurate, and they actually give us a specific success metric where the predictions, on average should be between 0.5 points from the true quality score. If it's anything worse than that, then they wouldn't take on this model because it poses too much risk for their business. So they have to be very accurate. So that's the background for us. And here we have the quality score, and these are all of our features now that are associated with that quality score. So we have things like the wine type, the alcohol content, and so forth. So these are all features or properties of that bottle of wine. So that's what we're going to be using to predict our quality score. It's these features. And so last time we focused heavily on this feature engineering step, right? And just as a review here, this is a nice diagram to show us what we're doing with feature engineering. So we always get some kind of raw data, and then we have to write functions to transform that data into what's known as a numeric data matrix for all of these machine learning algorithms to be able to work in Scikit-learn. And in general, you have to have a target column. So that's what you're trying to predict. So in this example here, I have a purchase amount. That's what I'm trying to predict. And then you have your features. But for Scikit-learn, most of those algorithms, they expect all of your features to be numbers, so numeric only. So if you notice here at the top, we started out with a lot of text data in our raw data, so metro area, for example, and LinkedIn URL. And we did all of that pre-processing to get to that nice format at the bottom, where we have education MS, right? So that's an indicator 0, 1, if somebody has a master's degree or not, based on their LinkedIn profile, right? So a lot of potentially complicated steps to get that, but that's what we're working on here. And many times, if you do your feature engineering really well, it could mean the difference between a very poor performing model and an amazing one. So it's really, this is where a lot of people say that there's a bit of art to data science. And this is one of the aspects of the workflow where some of that art and intuition can kind of help out. You know, as you get more experience doing this, you'll start to realize that, you know, hey, maybe I should try to scale my variables for this problem because it makes sense in that particular context. All right, so the first step, before we go ahead and get started with engineering our data, we always have to make sure that we split our data into a training set and a test set. So here we want to avoid data, it's known as data leakage. And so with feature engineering in particular, you know, you never want to do feature engineering on the whole entire data set and then split it into training and a test. Because if you do it that way, what you've done is you've introduced some information from the training data into the test data. So that's known as data leakage. So it's really important to do all of your feature engineering on the training set only and just really exclude that test set completely out of the process. So in Scikit-learn, we have our function here, the train test split function. So that's going to take a features, you know, matrix or data frame first. So here I have as the first argument WINDF, and then I'm dropping the quality score column. So those are just my features here. And then for the second argument, I'm putting my target variable, the quality score. And here I'm selecting, I want 75% of the data to randomly be put into the training set. And this random state is for reproducibility. So this is if I go back and split this data tomorrow, I'm going to get the same exact split. That's also important for us. So this will return 4 things to us: our training and test for the features, which I believe is X here, and then also our target for train and test. So that's Y train and Y test. And then as a best practice, because feature engineering, you're going to end up usually having multiple steps, and just to keep, you know, track of things, it's really good practice to go ahead and build lists of all of your features by their data type. So what I'm doing here is I'm creating a list that's named numeric features, where I'm taking my features, the X train, I'm selecting only the numeric columns from that data frame, and I'm turning that into a list. And I'm doing the same thing for my categorical features, but this time I'm saying select all the object types. So that is Panda's way of specifying if something is a text or a category in a column. And so after I execute this code, I'm going to get 2 lists. So here I have my numeric features list, which is correct, right? We see all of our numeric features from our original data, and we have our wine type as our categorical feature. All right, so now we have all the building blocks we need. We have our training data, test data, and the different columns that we have to work with. So now I want to review, so this is from last time, of how we build these feature engineering pipelines. So the typical syntax for this is that you start off with a pipeline object. So this is what we imported from Scikit-learn. And what this pipeline object will take is just a list of tuples. And in those tuples, you have all of the steps that you want to carry out to process your data. And so that's what we have here. I'm calling this numeric pipeline. And here is the beginning of my list. So that's the bracket there. And then my first element there is my first tuple. And so here I'm labeling this step. I'm calling this Yayo_Johnson. And then I'm initializing this Yayo Johnson transformer object from feature engine. And what this does is it will remove all of the skewness in our numeric columns. And then for my second step, I'm going to go ahead and use the standard scaler to standardize all of our data. And then I remove the outliers for the third step. And the very last step is I remove correlated features. So I'm using this drop correlated features transformer, also from feature engine. Okay.
Hey, David.
And so, Yes.
I'm getting a question coming in just about, where these transformers come from. So if people haven't joined the second workshop, you can grab the links that are in the chat box right now, and you can watch a recap from the first one. But last session, we went over, the meaning and background behind how all of these transformations work.
Yes, and they are here in the very first code cell where I import everything under the feature engineering section. And so I've labeled them by what these transformers do. So outliers and scaling features. So they come from this package feature engine. And this is where you get all of these transformers. And you can think of these as just extensions of the Scikit-learn pre-processing module, because Scikit-learn also has a lot of transformers that help with common tasks. But this package works very well with Scikit-learn feature engine. And it has some really great extensions to allow you to do a lot of cool stuff. So that's where they're coming from. But yes, you could go ahead and look at Notebook 2. We went into detail about how these are used and exactly what they're doing last time. Okay, so if we go back to our numeric pipeline, the one thing I wanted to mention about pipelines is that it's also best practice to group your steps or create pipelines based on the data type you are applying them to. So the one downside about pipelines is that it'll take a label for the step and then the transformer, but you can't specify to which columns to apply that to, right? So that doesn't have that functionality. So what I've done here is I've grouped all of my numeric transformations into one. So I could simply just apply it to all numeric features, right? So every single one of these 4 steps are going to be applied to them. So that's how we build it. So here I'm calling this numeric pipeline. I go ahead, it instantiates my object here, and now it's ready to go. And these work in a very similar way to the Scikit-learn models. So if you remember from our first meeting and also our second, the main things that we have to use on those objects is a fit method and then a transform method. So what the fit method does is that's what we're doing here in this next step, is we're taking this pipeline and we're saying fit this feature engineering pipeline on our training data, but just the numeric features there. So here I'm subsetting it here. So what it will do is it will go through, it will learn, this is how I remove skewness, this is the mean and standard deviation of each column of how I can scale, this is how I should be removing outliers from the training data. So it learns all of those transformations that it needs to perform. And that's what happens with this step here. So it's not that exciting. All you get back is, just a result of, hey, this is what I did, and now I'm trained and ready to use. Now, a nice feature in pipelines is that you can use another method that's called get feature names out on this pipeline. And it will tell you that after performing all of those transformations, these are the final feature names that are left in there. And notice that density has been dropped, right? So we originally had a column in our data that was density, but it was highly correlated with other columns. And so this last step, this remove core, it actually went ahead and just kicked that column out because it was too correlated with all the others. And so this is what we get as our final columns after our transformations are done. And now just to show you how we can use this to transform new data once it's been trained with fit, I have this numeric pipeline. I'm calling the transform method on it. And here I'm just going to pass the test data set just to test something new. So we trained it on our training data, but let's see if it'll work for our test features here, X test. All right, and everything looks good. So we have our final columns here. Notice my skewness has been greatly reduced. Everything is between, roughly -3 and 3. That's the standard scalar that did all that transformation for us. So now we have a functioning numeric data processing pipeline that we could use. Okay. So this is for our numeric variables. And then for our categorical data, we have just one step. It's going to be a pretty simple step. In this case, all I want to do is create a dummy variable encoding for the wine type. And that had two possible values, red and white. And so here I'm creating this, what I'm calling categorical pipeline. So I'm building another pipeline object, and I'm going to label the step in this one as dummy encoding. And here I'm going to use the one-hot encoder for feature engine, and I'm specifying drop last is equal to true. So this means that if I have two categories, I'm going to get just one indicator variable at the end. It's going to drop the last one. And this is really just to remove that redundant information that we talked about last time in our feature engineering. Okay, especially, and this is really important for if you're doing regression modeling. So those are really sensitive to if you forget to drop the last column here and you get two indicators, one for red, one for white, your linear regression model will most likely fail to even calculate, because with that you're introducing 100% multicollinearity if you don't leave the last level out. But for other models, it's not as sensitive. But for regression, you definitely have to be careful. You always want to do the dummy encoding version. All right, so here we build it. And here, I also just want to show you, to remind you of that functionality, there's another method in Scikit-learn. It's known as fit_transform, where it does two things at once. So here I'm saying fit my categorical pipeline. That means learn how to create those dummy encodings and transform this data I'm providing to you all at the same time, just to see if it works. So we get two things for one. So here I'm going to test it out. I'm going to train it and test it out on the X train, but only using the categorical features, just that wine type column. And let's see what we get back. So we get back a data frame, and here we get that wine type white. So it's a 0, 1 indicating whether it's either white, and if it's 0 by default, that means it's red, right? So that's all we're going to do for our categorical variables here. And the thing that we have to do now is we have to combine these pipelines because we have these multiple column types in our data. So usually when you're doing machine learning, you're not going to have a data set that's just all numeric or all categorical. You generally have a mix, and then you want to do different pre-processing tasks for both of those types. But we have to have a way of putting things together into one pipeline. And so this is where the column transformer from Scikit-learn is going to come to our rescue. So this also produces a pipeline, but it's got extended functionality. And the way you build it is you start with the column transformer, and it's just like a pipeline. You have a list, and then you pass tuples into that list for the different steps. But the nice part here is I can put a label. I'm calling this numeric engineering, and I'm saying add my numeric pipeline to this step and apply it to my numeric features. So the third part of the tuple for every single step is where you tell the transformer, these are the exact columns I want you to apply all of this feature engineering in this one particular step. So it allows you to combine numeric and categorical processes all in one, and it will carry them out in that order and just combine everything for you in the end. So it's really a nice feature. So that's what I'm calling my feature engineering pipeline now. So everything is put together into one object with this column transformer. All right, so now we're good to go. So we have our feature engineering pipeline. And the first thing we need to do before we can use this is to train it. So we have to use the fit method on this. And here I'm saying feature engineering pipeline dot fit. And we always want to train it on our training data, right? So you always got to remember, you never want to train it on your test data. You never want to train it on the full entire data set. You always got to get all these transformations on your training data. So that's what we're doing here. So here, again, nothing too exciting, but it just kind of spits out a status for me. And it tells me, great, I did all of this stuff. So for all of your numeric columns, which you have listed here, I'm going to do all of these steps for those. I'm going to remove skewness. I'm going to scale them. Let's get those outliers out and remove correlated features. And then I'm going to move on and do a dummy encoding for the line type. And that's my whole entire process, right, that I'm going to use here. So let's test this out. So we fit it, we've trained it. So now we can go ahead and use the transform method on it to go ahead and see what we get. So here I wanted to save the result as a data frame so we could print out the transform data and then have a look and make sure it did everything correctly. So what I'm doing here is I'm creating a data frame, xtrain pipeline, and here I'm using pandas data frame to create a data frame. So for the data argument, this is what I'm adding here. I'm saying go ahead and use my feature engineering pipeline, transform my training data. And this is going to return a NumPy array. And so usually these column transformers give you back a NumPy array, which is okay. It prints nicely, but you can't really use the advanced features of Deep Note to go ahead and explore like you would a data frame. So all I'm doing is converting this to a data frame. And that's why here for the column names, I'm saying there's my pipeline, and I'm using that method here, get feature names out. So that's going to tell me what the final names of those features are. Okay, so let's have a look to see how it transformed our entire training data set. So like I mentioned last time, this is just beautiful to me because everything just looks great. I don't have any skewness. All of my columns are in the same range if they're numeric. And then my line type is an indicator if it's white or not, right? So it would be red, but everything looks great. So this is exactly what our models need for Scikit-learn. So now we're at the stage where we've developed this feature engineering pipeline, it's trained, and I could go ahead and transform my training data, my test data. I could even do the whole entire WineDF now. It'll work on anything that's got the same format. And now we're ready to go. So now we can go ahead and add our model to it because we've prepared our data. And then here, I just wanted to demonstrate that it'll work on any input data that's got the same columns as your original training data. So here I'm putting X test in there just to make sure that we get the same results here. And here I wanted to take a moment just to talk about that data leakage concept that I mentioned before. So in this step on our training data, what we did for scaling, right, in our feature engineering steps is let's just focus on alcohol, for example, here, this column. It looked in our training data and it calculated the mean and standard deviation of that original column, alcohol, in our training data. And it's that mean and that standard deviation that it's always going to use those to scale any new data coming in. Right, so it's really important to do things that way. Because if we think about it the other way, let's just pretend we did feature engineering on the whole entire wine data set. So if you look at that whole entire alcohol column, our feature engineering would have calculated, okay, so what's the mean and standard deviation of that column? And that's what I'm going to use to scale the data. And then if you split that data after doing that into training and test, then you have to think about, well, what does my test data now know about the training data that it didn't before, right? So it knows something about the original mean and standard deviation of the data, right? Because we use the whole entire data frame to calculate those. And so that's a way that you've introduced information, from your training data into your test. And that could lead to really bad, it's called model generalization, where on new data, you might think your model performs really well, but when you really try it out on brand new data, it does very poorly. So that's just one example of how this data leakage can happen. And but you'll be fine if you go ahead and follow our methodology here, where you split it first, and then you only do your feature engineering training on your training data only. But everything looks good. So our feature engineering is all set, and we are good to go. Now, the other awesome thing about these pipelines in Scikit-learn is that it's not limited to just data preprocessing steps. What you can also do is you can add an actual model object as the very last step in your pipeline. And so that's what I've done here. I'm calling this linear reg workflow, and I'm building another pipeline. And the very first step I'm saying is do all of my feature engineering. So if I give you data, make sure to transform it and prepare it just the exact same way that we did in the previous code chunk. And then after you do that, in the next step, I want you to fit a linear regression model onto that transformed data. So this allows you to bundle your feature engineering and your modeling into a single object. And this single object here has the fit, transform, and fit transform methods like before. So you could use it just like a regular model object, but there's a lot going on here behind the scenes. So let me go ahead and define this object for us, this pipeline object. And it's really amazing. I wrote down these steps, right? That this is what's going to go on behind the scenes when I call fit on this pipeline here. It's going to train my feature engineering steps, right, on the training data. It's going to transform my data, and it's going to train my model on my transformed data. So it's doing a lot for us in the background. And so what I'm doing here is I'm saying linear reg workflow, and I'm calling the fit method. But this time I need to provide more than just the training, the X training, right? I also need to provide Y train. I need my labels, right? And why do I need that? Is because the last step is a linear regression model. So it has to know what the truth is to be able to find the optimal model parameters for that. So here, and if I hit play here, all of these steps here are being carried out. These three really important steps were just carried out for us. But again, we don't get too much exciting stuff at first. We just get kind of a message here that displays, hey, this is what I did, and I trained your pipeline. But in order to use it, now we could use the predict method. So if we have a model in our pipeline and we have used the fit method on it, now it'll actually work to predict, what the possible true labels could be of our quality score. So here I'm going to use it to make predictions on my X train. So let's have a look. And this will give me back a NumPy array with the model predictions. Okay. So what it did here for us is it took our original X train, which is not transformed. It went ahead and transformed that data and then used our model to give predictions on that transformed data. And now we have our result. So it's really cool. I mean, this column transformer, how you can combine everything and put your models with your feature engineering steps, you can do a lot. And you can imagine where if you wanted to try different feature engineering processes mixed with different types of models, all you would really have to do is just create a couple of these pipelines. Maybe this other one, instead of linear regression, we might try something known as lasso regression, which we're going to talk about in a little bit. All I would have to do is replace this last step and call, now I would call this my lasso regression workflow. And I can train that as well. Or I could create another feature engineering pipeline where I try different combinations. And again, it's nice that you can bundle this into one object and then just go ahead and use the fit method on each one. And then you could easily compare them. So it's very nice feature.
David, I've got a question coming in on that as well. It's a hard one to answer because I think, like you just mentioned, you're going to experiment and try a lot of the different combinations. But the question is, how do you know when you're done?
Yes, and that's a great question. If you didn't have a success metric, you would never know when you're done, because you could forever keep trying different combinations of this and tweaking it and seeing how much better it gets or not. But generally, the process is, if you have that success metric, which we do, which says that if you are on average, less than 0.5 points off, then that's great, right? So then that's how we know when to stop. And so for me, I always like to look at what is the simplest model I could find that will meet that objective, right? So you always want to start simple and then try more complex models. But when you start simple, you always have to check, did I meet that business objective? No. Okay, well, let's try maybe something a little bit more complicated. And that's how you iterate through. And you can get to a point where you may not be able to solve, your success criteria, because sometimes there isn't enough information in your data to give you that amount of prediction accuracy. So that's when you would know also to stop and go ahead and try to maybe collect more data to make things better.
And that's a great example of why it's so important to have that business metric in your mind before you start this process, so that you can reach a stage where you're like, okay, for now we are done with this. Great,
Yes.
thank you.
Yes. Yeah, really, really good question. Okay, so let's go ahead. I wanted to show you how you can evaluate how your model did, because here we can't really see that. If we use the predict method on our workflow, it gives us all these predictions, but how do we know they're good? So this goes back to our first meeting. So this is from our lesson 1, where we built our first regression model. And there I showed you this object here. It's called prediction error from the yellow brick package. And this creates what's known as a predicted versus actual plot, so we can see how well our model is performing. And the way you set this up, this first, the second line here is optional. I'm telling matplotlib to make the figure an 8x8, just to make it a little bit larger for you guys to see. But here you go ahead and into prediction error, you can pass your workflow, the pipeline object here. I'm going to say, is it already trained? Is fitted? Is true? Yes, we already trained it. And then here, I'm setting best fit to false and then alpha to 0.3. So I'll talk a little bit about when we see what the plot is. So once you instantiate this object here, all you have to do to see how well this model performs is use the score method from it. And I could pass in the training data, or I could pass in the test data, whichever one you would like. Here I'm doing training. And then you call the show method. And then this is going to display that nice actual or predicted versus actual plot. And here, this is really the only thing you need for the most part to evaluate regression models. It's a very informative plot. On the y-axis, we have something that's labeled as y hat. That means what is your model predicting for that particular row or observation. And on the x-axis, we have y. That is, what is the truth? So in our training data, my x-axis here is the true quality score. And then my y-axis here is my predicted quality score from my model. And we did extremely well here, right? We got an R squared of nearly 1. So if we round that, we get a 0.99. And all of the points are very close to that dashed line, which is the line y is equal to x. So that is telling you that your predictions equal the actual values, right, on that line. So the closer the points to that line, the better your R squared value is going to be. And in this case, we did really, really well with all of our feature engineering. It was really able to capture all of those, all that information in there and give fantastic predictions. And if we compare this to, I should have probably pulled up from our first lesson, we used only alcohol. And I believe our R squared was 0.38 on our training and test data. All right, so adding all of these other features and processing our data correctly, it's a completely different model now, right? I mean, just a huge improvement here. But again, this is not good enough, right? So R squared, it may be great, but we have to make sure, did we meet the business objective though, however, right? That's ultimately what we have to answer. And for that, this is also from our first meeting, we have to go ahead and use something known as the RMSE, the root mean squared error. And that represents the average error that your model will make in a regression model. So we're using this mean squared error function from Scikit-learn. We put in the truth, which is our Y train. And then I'm using my linear regression workflow and I'm making predictions on my X train. So I'm getting my predictions and I'm saying squared is false. And this is what we get. Okay, so what this means is our average error is if I round, 0.13, right? And in our business objective, it has to be 0.5 or lower, right? So now we know that we have met that business objective. So kind of on average, you can think of this as if I make a prediction with this model on the training data set, I'm going to be off by about 0.13 on my quality score. So if the truth is, 7.1, I'm going to predict maybe 7 or 7.2, kind of on average. And that's really great. And you can kind of see that here in this predicted versus actual plot as well. Most of those points are very close to each other and they have great agreement here. Okay, so this takes us to our next section here on cross-validation. So whenever I get results like these, the first thing I will ask myself is this too good to be true? Right, so we met our business objective, fantastic R squared, but was it just random luck? Did we just kind of win the lottery by chance? And that can happen because if you split your data with a train test split, and what if it happens to just split your data so that in the training data set, you have all the really informative rows and you get really great performance, but then it happens that on the test data set or maybe new data that you get, it doesn't work that well, right? So that can happen. So that's the downside of using a single train and test. Iteration is because you only get one estimate of model performance, right? Which I like to have a lot more than that, just to feel confident that this model is what it says it is. So one way we can increase our estimates of model performance is by using cross-validation. So we have to take an extra step here. So we take our original data, we split it at random into a training data set and a test data set, but then we do one more split. We take our training data and we split that into what's called cross-validation folds, right? So we partition that data up randomly into folds. And this is typically either 5 or 10, or could be up to 20. And then what do? So for each one of these folds that are a subset of our training data, we will go ahead and we'll hold out the first fold and we'll train our model on the remaining folds and then get predictions using that first fold that we left out of the process, right? So that way we get one estimate of our performance. And then we keep iterating through the folds. So now I'm going to use fold 1, 3, 4, and 5 to train my model. And then I'm going to make predictions on fold 2. So now I get another estimate of how my model performed, right? And I keep cycling through all the way until the end where I get to my last fold. And that's what I'm using for my performance evaluation, right? So if you do 10-fold cross-validation, it's going to give you 10 estimates of how well your model did. So instead of getting 1 R² like we did, you're going to get 10. And that is definitely better than 1, right? Having 10 estimates is always better than having 1, just to see how your model is doing.
How do you know how many you should do?
Again, that's kind of the art aspect of it as well. The one major consideration you have to think about is how expensive and time consuming is it to fit one model. So that really depends on how much data you have and how complex your model is, right? So if it takes you 5 hours just to do one iteration of training, then you probably are just going to do 5 folds, depending on how much time you have and how long you can keep up, your AWS maybe resources, for example, if you're doing cloud computing, right? So how much money you have to spend on that model training. So that's typically the the main criteria. But for us, of course, the more the merrier. I mean, if this thing was quick, I would do 1,000 iterations just to get as many estimates as I possibly could. But usually you're held back by data size and time. That's kind of your main thing. So it's very easy to do this in Scikit-learn. So how can we do this cross-validation? How can we get, maybe 5 estimates or 20 estimates of my model performance in my workflow? So there's this built-in function. It's known as cross-val score. And I'm using it right here. And I'm passing in my workflow. So that has my feature engineering and my model. And I'm passing in my training data, my X's and my Y's. And here I'm saying CV is equal to 20. So here I'm going to do 20-fold cross-validation. So it's going to fit this workflow 20 times and estimate how well it does on a held out fold each time. Now I'm going to save this in something called linear workflow CV scores. You get back this NumPy array with all of your performance metrics. And by default, if you're doing regression, it calculates the R². So if I print this out, I get this nice NumPy array of all of my R² values that it estimated for each one of those 20 folds. So now I have 20 estimates of my R². And now I can go ahead and turn that NumPy array into a pandas series. So I'm doing pd.series. And I'm using the describe method to go ahead and calculate all my summary statistics just to see what I'm working with here. And I can see that my minimum was 0.97, maximum was 0.99. So everything was consistently kind of falling in into a nice range. And the standard deviation was very low. So the data wasn't spread out very much. Here I'm making a histogram of that series just to visualize the scores to see how well we did. And everything kind of bunches up around that 0.99. So everything's very consistent and it's got low variability, which is great. So that gives me more confidence that what I found the first time wasn't just a random accident, that this model actually might be really good, right? So that's what this cross-validation is used for.
And I guess it also is showing you there that you have one of the R² values coming in at 0.97, which is a little bit lower. So you're saying that could have been the one that you did the first time, and you would have thought that this is kind of how I should evaluate this model, where by doing it over and over again, you're getting is clustering around what you believe is the underlying accuracy of this, right?
Yes. And you have to remember during this process, you're putting on your statistician hat, really, right? You are trying to answer the question, is how well is this model going to perform on the population, on new data I get in the future? And so you want to have as many of those estimates as possible. And whenever I teach a GMU and this topic comes up, I always say, well, okay, what if I took a random sample of one student from GMU and I asked for their GPA? And they told me 4.2, right? So extremely well, right? How comfortable would I be making that inference on the whole entire population at GMU that they all have 4.2 GPAs, right? So you need more. I would need to sample probably 100 students just to get a really good distribution of what it's really like out, in the population. And we're doing the same exact thing here, right? So the more samples you have, the better, and the more confident you can be that your model is what it says it is. Granted that your data wasn't collected, there's no issues there, or it wasn't biased in collection, right? So there's a lot we could talk about on the statistics side of things, but maybe we can save that for another session, just because there's a lot to discuss there too. All right, so here I am taking this linear reg workflow, but I'm going to make my predicted versus actual plot on the test data. So this is the ultimate test. So no matter how well you think you did, right, on your training data, the test data set is something brand new. And this is where we can really test, does this model say, is it what it says it is? So let's have a look. And it is. So it didn't lie to us. So we gave it brand new data and we got the 0.99 R squared as well. So it matches very well to what we got in training. So at this point, I would feel very confident that this is a good model, right? And it meets our business objective, and we would be ready to go. And it's relatively simple as well, just a simple linear regression model. And then here I'm just testing my RMSE on the test data set. Is it less than 0.5? Yes. So that also checks all the boxes, right? So just an example here of just how you can take a model that didn't perform very well and get it to be a very high performing model with some really good feature engineering and cross-validation. Now, I always like to end these with a new topic that we're going to be going into more detail next time, especially when we start doing classification. We're going to be doing something that's called hyperparameter tuning. So I always like to put this here at the end just to maybe confuse people a little bit, just to give them a reason to come back next time, because we're going to go over this in detail in a different context as well. But what I wanted to introduce here is a different version of linear regression. So we've been doing the standard linear regression, where we simply just, for each column in our data, each one of them gets a coefficient that it gets multiplied by, and we add them all up, right? That's the simple linear regression. And the way that this model knows how well it's doing is by something known as the sum of squared errors. Okay, so this is it's known as a loss function. And you simply take what your model predicted, and then you subtract what the truth was in your Y train, you square it, and then you sum it up across all the rows in your data. So that gives you the total error of your model for that particular line that you fit. And that particular line is determined by those coefficients that your model has. And here's a nice visual of what that looks like. So if you have a regression line, everything that falls on that line is going to be your Y hat. That's your predictions. And then you have your real data in your training or your test maybe. And the difference between the vertical distance between those two things is your residual. So you take the difference of those two. So you simply add up all of your residuals, and the linear regression model is trying to find the line that you can put in between those points to minimize all those vertical distances across the whole entire range. That's what the typical linear regression model is doing. But the lasso is a little extension. What it does is it adds a penalty term to this sum of squared error here, this term, where you simply just sum them all up. And what it adds is this term, it's alpha, which is a number that can be anywhere from 0 to infinity. It's called the regularization, parameter. And then you sum up the absolute value of your coefficients. And so you can think of this as my normal error plus a penalty, because the larger my coefficients get in my model, the more of a penalty that I get in my fitting process. And the mathematics behind this is very interesting, but it has the very nice property where it can do what's known as kind of automatic feature selection, where it can actually tell you that certain of those parameters, those betas, should be set to 0, like exactly 0, because the information in those columns isn't helping you out at all. So it has that nice property. But the one thing we need to do, though, is to use this model, we have to figure out, well, what alpha should I use to do, which one would be the best? I mean, 0 to infinity is a huge range. So what do I choose? And so this is what's known as the hyperparameter. So it's something that you have to set before you fit your model. And most of the time, you don't really know what it should be. So what we're going to do is the typical thing you want to do is use cross-validation and then a special grid search in combination with that to figure out what's the best possible alpha. So let me just show you how this is done. And then we'll expand on this quite a bit in the next, lectures in the series. So here I am creating something called lasso regression workflow. I'm using the same feature engineering pipeline, but this time instead of linear regression, I'm doing a lasso regression object, and I'm setting the default value of that alpha to be 1. So that's kind of my penalty term strength that I'm setting to. And then the next step for hyperparameter tuning, you always should have a grid of values that you want to test for that particular hyperparameter. And this is a Python dictionary, and you always have to have it in this format right here. If you have a pipeline, it should be the step name, 2 underscores, and then what parameter you're interested in. So here I'm saying lasso regression, so that's my step 2, and then double underscore alpha. So that is this parameter of the lasso object that I want to test. And here I'm putting in the candidate values. I'm going from 0 all the way up to 0.7, let's say. I just want to try these out. So I've made my grid here. And for some, why am I not able to execute this?
I think your workbench disconnected.
Oh, maybe I was talking too much and it disconnected. Oh, wait, there I am. There's 2 of me. Okay. All right, so let's see if it works now. Yes, it does. Okay, so I have my dictionary here. I'm calling it my alpha grid. And now I can use this method, grid search CV. So this is also a Scikit-learn object. So I'm passing in my workflow, the lasso workflow. I'm giving it a grid, and I'm saying do cross-validation of 5, do 5-fold. And so what this is doing behind the scenes is for every single one of those alpha values, let's say we start with 0, it's going to fit the model 5 times and give me 5 performance estimates using cross-validation. And it's going to give me R² values for that particular value of alpha. And then it's going to cycle through the remaining values I'm testing. So what I have to do once I've defined that grid is fit it using my training data, my X train and my Y train here. And now it's performing all of those tasks, right? So for each alpha, do 5-fold cross-validation and see how my model performs. And after you're done, you can access these special properties of this lasso tuning. So the first one is called best params, and then another one is called best score. And so this will tell you which value of alpha performed the best and what was its corresponding R-squared score. So for us, it was 0, and 0.99 was the R-squared. All right, so that's how I was able to try these various values of alpha to see which one worked the best. And if you ever want to get into the gory details of what was done behind the scenes, you can also access this object here, CV results. So that's a dictionary. And these are the important keys. So we have the params, the mean test score, and the standard deviation test score that it got. And this will make more sense when you see this printed out here. Right, so here I go from 0 to 0.7. My second array here is what I get for my R-squared values on the held out fold, right? So it's averaged all those 5 performance estimations for that particular level. And so you can see I go from 0.99 if I round, all the way down to basically 0 if I have the regularization of 0.7 for that particular value, right? So that one didn't work very well at all. And then I also get the standard deviations associated with each one of those because I have 5 estimates for each one. All right, so if that's confusing right now, that is absolutely okay, because we're going to do a lot more examples in classification. This comes up quite a bit, and it'll all make more sense. But I just wanted to introduce this to you guys today about how you would go about, if I have this hyperparameter, how do I go about choosing what the best value is? And it should always be based on your cross-validation performance. And then you have to always have a grid of values that you need to evaluate to see, what would happen. All right, and I'm proud of myself. I didn't go over too much today. So
that was fantastic. And I think the most practical point of view is that the first 3 weeks or the first 3 sessions that we've done have been about predicting a number, right? We've been doing regression models here. We're looking for that average score or that predicted score of quality for a bottle of wine. When we move forward into classification, we're now going to be trying to predict different labels. And I don't know exactly the examples that David are going to pull together, but with this data set, maybe you could predict white wine or red wine based upon the other numeric values that might be in the data set. So it's another practical applied business purpose. We're out of time, but I see one more question coming in. Do we have to change test and train data when we rerun any of the algorithms?
No, so if you were doing it manually, you would have to worry about all that stuff. But the nice thing about the pipelines is a lot of that complexity is handled for you. So it will go ahead and take your training data. It's going to split it up into all the folds, and it's going to train your feature engineering on each fold. So all those kind of best practices are built in already in the pipelines. So that's one great thing about those is you really don't have to worry about too much, right? Unless you do something that's very unique and special.
Yeah, and the other question that's come up a couple of times has been about careers. And, we're not focusing this discussion on kind of what you're going to be able to do, but I've heard from a few people who are young in their career. They're looking for that junior data analyst or junior data scientist role. And especially remote work was a question that was coming up. And the ideas that I threw out privately to somebody were right now, at least on LinkedIn and AngelList, for the first time, you can filter because of the reality of COVID by, hybrid jobs that are both in-person and offsite, fully remote or fully in person. And you can also filter, as you've always been able to do, by the level. So, junior or entry level, mid-level, senior level, et cetera. So starting with that combination just to see what is around and what might be interesting to you. But then also from a practical point of view, somebody mentioned the online certificates you can get from a Coursera or from a data camp. And they're fantastic and they're good to do, and you can learn a lot. You can learn so much for free today, as you all know, on YouTube and other venues. But you also want to have some way of taking something tangible from these experiences, whether it's putting up code from a project on GitHub, having a working project that you can send a link to a potential employer so they can see what you've done, maybe on data visualization, or maybe you put a machine learning model into production. So there's so many ways that you sort of stand out from what is becoming a more crowded entry-level position for data science, I think, today. I'll give you just one example, and then I'll let David speak if he has any more. But when I moved to Amsterdam from the United States in 2016, I was going to a startup company from a more traditional research and data background. And one of the ways that I got my foot in the door was by scraping their website using R and then analyzing all the data that I was able to grab from their site as part of my kind of application process. So this was me showing a real practical application of using web crawling to say that I'm going to be able to contribute, I hope, to your organization based upon some of the items and activities that you're working on. David, do you have any last minute thoughts on that before we sign off?
Yeah, I mean, the important thing is to focus on, I think, problem solving in data science. A lot of times people get hung up on the technical skills and do I know how to fit a model with Scikit-learn and this and that, but it's really about how you approach problems and your thought process, right? Is how do I approach feature engineering? What's the best way to solve this problem? Do I have a success criteria, right? Do you have that in the back of your mind? That's going to make you stand out in any interview, is the way you think about these problems and how you solve them. And also, I think more and more these days, having knowledge of cloud concept is very important. So it doesn't matter which cloud it is, AWS, Azure, Google, but having that skill of maybe being able to take this Python model and put it up into AWS and have it be serving predictions on call in real time, which is something you guys could do. I mean, AWS provides free training for that stuff on their website. But that will also make you stand out because more and more these days, data science is moving to the cloud. I rarely meet people who are on a data science team who are just working off their laptops only. You know, you're putting things out into production in the cloud these days. So the more you can learn about that, I think the better off you will be. And it's never too early to start with that.
Yeah, great points, David. Once again, thank you for your time. Thank you, everyone who joined both on Zoom and on YouTube. We are back at it next month. I believe the 1st of October is where Saturday falls. So you'll be able to sign up from the links. I will ping people for those who I have emails for to sign up for the next session. If you have any more questions, feel free to reach out to us. You can reach me at alex@dataquery.com or david@dataquery.com. We really appreciate it. Thanks so much for the comments coming in. We appreciate that too. And we will see you.